first morning session on the equation of state of neutron-rich nuclear matter, clusters in nuclei and nuclear reactions. Our first speaker in this session is YENNELLO from Texas A&M. She's going to tell us about the constraining equation of state of asymmetric matter with high-value collisions. Sorry.
No. Yes. Yes. Okay. All right. So I'd like to thank the organizers for inviting me to come and give this talk. And I will attempt to talk not just about work of my group, but sort of the work of the field. And for everybody who I'm not representing your work, I'm sorry. And everybody who I'm misrepresenting your work, I'm more sorry. No. But what I'd like to do, since this is a broader audience than just the equation of state crowd, is to give you some introduction to sort of what we do, why we do it, and some smattering of the data that's out there and the calculations that help us set constraints on the asymmetric part of the equation of state. And there's going to be lots of talks. There have been lots of talks. There's lots of people that are experts here on the individual measurements, and so I might encourage you to seek them out if you have particular questions about that. If we really only wanted to learn about what happens for nuclei that are in their cold state, we could look at just binding energies, or we could look at the GMR, and we could understand what happens when we don't have the number of neutrons at cold normal nuclear density. And so if you want to get away from normal nuclear density, if you want to get to warm or hot nuclear systems, this is why we need nuclear collisions. And so this is just a calculation, an IBEU calculation, to show you what happens in a mid-impact parameter collision. Okay, so why do we care, okay? We care about the nuclear equation of state because it's related to, well, everything, okay? So for either talking about atomic nuclei, or you're talking about neutron stars, you're talking about the neutron skins, or you're talking about supernova. We need one equation of state that has to describe it all. What we really can't do is to say, well, this equation of state taken with this set of data and this particular model with this one observable describes the equation of state, and then pretend that extends to everything. So what we really need to do is to be working as a community, and we have been working as a community, and that's what I hope to portray to you today, to look at this from many different aspects. Connects what's really at the heart of what we're doing, which is looking at the isospin dependence of the strong interaction, okay? So we'll talk about the symmetry energy, and you'll see I'll use words like stiff and soft, and we'll have these very underlying strong interaction. All of these observations, astrophysical observations, are also affected by the symmetry energy, and the thing that kind of connects them is this many-body theory, where you then have the symmetry energy. So you can connect the symmetry energy that needs to explain this with something that is consistent with these observations, really all based upon the strong interaction, which is really kind of where we want to, what we want to understand. Okay, so just the quick slide that sort of says, okay, so if you have neutron matter or nuclear matter, so in terms of just saying either I equal 1 or I equal 0, the difference between these two curves is your symmetry energy here. And these are various different predictions of different models, and I don't want to focus on those in particular, but just to kind of let us look at, so we can look at symmetric nuclear matter, or then we focus here on the symmetry term, where it changes as we go away from n equals z nuclei. If one looks at this curve here, I bring it up only to talk about this stiff versus soft, so that you'll know what I mean when I use those terms. And so if you look at the symmetry energy as a function of density, for some calculations, it actually bends over, okay? And so when that actually curves down, we call those soft, okay? So when you see something that says soft or as-soft, what we're talking about is curves in which the symmetry energy actually decreases at high density. And for stiff, these curves where it becomes linear or supralinear, and it continues to rise as a function of density. So initially we talked a lot about stiff and soft, and as the field has evolved, what you'll see more is constraints now in terms of L and S, okay? So what we really need to be talking about, because you'll see there are multiple, depending upon which calculation you're talking about, stiff means different things, okay? And soft means different things. And so what you'll see now, and you'll see this toward the end, is that we try to describe these curves in terms of S and L. So the value of the symmetry energy at normal nuclear density, and then what is the slope, and then you can even say what is the curvature, okay? But to get much more quantitative, you'll see these values of L show up later, and the final plot I'll show you that shows all of the constraints put together will look at S and L. Okay, I need to give you one caveat here, is because when I was showing you all these nice curves, right, they're all nice, fairly smooth curves, and when you look here, they're all coming right down here to 0. And so that works if you go ahead and use a parameterization for the whole thing. But we do actually have some data from Joe Nadowitz et al. That says you really have to, when you get to very low nuclear density, it doesn't go to 0, and it's not a smooth thing. So this is, I'm not going to spend a lot of time talking about this because I'm going to go back to the overall looking at the curves, but I need to put that caveat out there that as you get to very low densities, you have to worry about clustering, and then you have to do things a little bit differently than you would look at for the whole curve. Okay, so if we dial back again, and I'm going to wander so I don't ignore this side of the room too, to how did we learn anything about the equation of state, and sort of some of the early work before we, or as we started to worry about the symmetry energy, was some work done by Pavel, Roy Lacey, and Bill Lynch, where they took the gold plus gold flow data from the Bevelak and said, if we look at all this flow data, what can we learn about the equation of state? Because when you talk about flow, it should be sensitive to this equation of state. And they took all this data and they put it together, and they were able to put this constraint on there, okay? Now this constraint is at relatively high density here, because this is the hatched area here only goes down to 2 rho over rho 0. But it was sort of the first constraint that was able to be put on that was able to throw out, in some sense, some of the very extreme equations of state. That's just looking at sort of the symmetric part. So then you have to go and say, what happens as you then put in this as a stiff or as a soft, and then you add in some more uncertainty, okay? And so we have to then try to answer that uncertainty. And so one of the things that I will show you that we've used to try to address the asymmetry term is also the flow again. So you'll see that along with a number of different things. One of the first observables, I think, that we tried to look at in terms of trying to pin down the symmetry energy was looking at fragmentation, okay? So if you have a hot system and it fragments, the identity of the clusters will carry information about the symmetry energy. And there was some nice theoretical work by Baran that showed us that the neutron richness will go into the low density phase, and then your bigger fragments will come out of a more symmetric phase. if you then had those sorts of things and you looked at isotopically identified clusters, you could use a technique developed by Betty Sang at MSU called isoscaling. And so the isoscaling looks at the ratio of fragments from two different systems that have a different N over Z. And so you can go ahead and use this isoscaling technique, which then, if you know the temperature and you can properly account for all the secondary decay effects, you can connect back to the symmetry energy. And so that's sort of where we first started looking at these isotopically resolved fragments and saying, can we learn something about the symmetry energy? A couple of things happen there in that, A, we have reacting systems, and then there was some nice work by Sarah Winchell that said, if we can actually reconstruct the system, because we can pick up all the pieces, then we can really know the system that breaks up. So you'll see both things where we say, this is the system that reacted, and we've put enough constraints on it that we have some understanding of what the N over Z of the system was. And the other thing we can do is actually collect up all the pieces and say, this is the system that broke up. And that's what Sarah Winchell did. And when doing this, then she extracted out, so this comes out of the isoscaling, where alpha over delta should be related to C sim over T. And if you look at alpha over delta as a function of the excitation energy, you see this decreasing. So the excitation energy is decreasing, your temperature is increasing, but you start to be able to measure things based upon this isoscaling. A number of different measurements were done by a number of different groups, both measuring directly and then in comparison to models. So you would run a model with a different symmetry energy in it and compare the fragments that you have measured with the fragments that the model would predict to try to say what's the symmetry energy that is necessary to describe these fragments that have been experimentally measured. And so a number of different groups have done that and really started to put some of those initial constraints on. And the other thing that we learned through some of this is that the symmetry energy seems to decrease as a function of colliding energy, beam energy, excitation energy. And so then this decrease in the asymmetry energy got related to thermal expansion by a number of different, by a number, now I'm in trouble. I can't go backwards, can I? Yeah, okay. Can be related to this thermal expansion. So now we can start getting at what does the equation of state look like, because if we can measure the symmetry energy and we have some idea of the density, we can start to put this together either in a model-dependent or a model-independent way. We really can't do anything in a model-independent way. Okay. Another way in which the symmetry energy was extracted out of data was to look at this Landau expansion, again looking at fragment yield ratios from systems. These were reconstructed systems, again, so one could make cuts on what is the MS, which is really the source isospin. And actually what you see here is that the values of C sim over T as a function of excitation energy line up very well between this Landau expansion and in terms of isoscaling, so both the yield ratios and the isoscaling. So again, these are sort of more direct measurements rather than just in comparison to pick a symmetry energy in a model and run the comparison and compare it, the result. So one of the ways in which there's been a lot of progress, I think, in probably the first sort of extraction of what is the density dependence of the symmetry energy really comes from work out of MSU that was spearheaded by Betty Sang, looking at isospin equilibration or isospin diffusion. And so there's kind of a history of the isospin equilibration work, and you can do a number of things. So if you have a projectile and a target and they come by and they have a different neutron to proton ratio and they interact and they exchange nucleons, you have some nuclear transport, and then they separate, and then if you can measure the N over Z of the fragments that after that interaction, that process of equilibration or diffusion is sensitive to the symmetry energy, so we can try to extract it back out. You can do this a couple of different ways. You can look at different isotopes. So the very nice work done by Betty up at MSU was tin on tin. Okay, so you use just different isotopes of tin, tin 112, tin 124. Other work has been done using isobars. Okay, so you can triangulate this in multiple ways, but the idea is to control the N over Z of your reacting systems and measure the fragments that come out. You can look at yield ratios, or then you can use this isoscaling technique. Any of these that get back to sort of what is the fragmenting system are useful and can be plugged into this isospin tracer method that was developed, that came out of the FOPI data that really was looking just at stopping earlier, and we heard about that earlier this week already. So the isospin tracer method is here, and you just need systems that you can anchor and then across systems, and the question is, when you do your cross systems, how close do they come to each other? So if you use tin 112 on tin 112 versus tin 124 on tin 124, those should be your anchors. And then the 112 on 124 versus the 124 on 112, do they come to the same answer, and is it halfway in between? Okay, so like I said, very nice work. That was, oh, and you can look at Pavel Danielovich actually did a nice job of doing a lot of the math in terms of the drift and the diffusion and separating those out in terms of saying you have diffusion that is dependent upon the isospin concentration. So if you have this different N over Z of the projectile and the target, you should have diffusion between them. But you also have to realize that you have drift, because if we form a low density neck, then you have migration due to a density difference and not just to an isospin difference. And so trying to separate these out is again something that we have to work on. Okay, so here is this data that came out of MSU in 2004 based upon the diffusion, the isospin diffusion in tin 124 plus tin 112 data. And so now what you see here is a comparison done with an IBUU calculation that then looks at these different gammas are the different stiffnesses of the equation of state, okay? So they're just going from very soft to very stiff. And what you see is the data is in agreement with neither the very stiffest nor the very softest, but something that is near linear in here. This data actually has been compared to a number of calculations, and I don't really have time to show them all, but it's been really nice to start to put some constraints against the model calculation. Some more recent work that was done by Larry May kind of looks at what happens as a function of impact parameter with the ASI-soft or the ASI-stiff with this IBUU, and you can see that for your ASI-soft, you equilibrate much faster in terms of looking at your impact parameter. You're going to get your equilibration. You also end up in a different place because you have this drift into the neck, and when you're looking at just what's left in the quasi-projectile, that depends upon what you lose to the neck. And so that's something that we haven't spent a lot of time really worrying about what was going on to the neck in the isospin diffusion work, and it's something we have to take into account. Here's some SMF calculations in comparison to, again, that very nice MSU data. And again, one can see that you have the lower energy that gets to equilibration faster. That's consistent certainly with earlier data on equilibration, where you can see the equilibration achieved in sort of 35 MeV per nucleon, but not 45 MeV per nucleon. 5 minutes, okay. Now we're in trouble. Okay, we can go ahead with that SMF work and be able to try to separate isoscalar versus isovector effects and see that R is really much more dependent upon the isovector part of the interaction. Comparison of some of this isospin equilibration, the calculation to some Indra data, and you can see here, this is the data from the PLF, and the stiff or the soft calculation, so that you can see there's possibly a better agreement with the stiff calculation. Some work, so what a lot of what's been done is to look at small clusters, intermediate mass fragments that were attributed to the projectile-like fragment to understand the projectile-like fragment. Zach Coley up at MSU used a device that really isn't normally part of our discussion, which is the Mona Lisa array coupled to the sweeper magnet to go ahead and directly detect the PLF. And so when he looked at the PLF, then he's able to put some constraints running COMD for various different asymmetry energies, and again, coming up with this idea that L in the vicinity of 80. Very nice work then. Once you're talking about, you have both this drift and the diffusion, you can have, you're looking at the equilibration between the projectile and the target. The group at Indiana then said, well, if I have a projectile-like fragment and it's deformed, maybe I can look at the equilibration right within it. And so they use the PLF by itself to be a probe. And so if you have your target-like fragment, you have your separation, but then this is not a uniform thing. You have some neutron richness, because maybe that's a neck that's been reabsorbed into the PLF, and you can watch as this thing rotates to see the equilibration between that neck-like thing and the PLF. And so they've actually done this by looking at the angle of rotation and being able to watch the equilibration and connecting that to the stiffness of the equation of state. And again, some more data along those lines where you can actually see this equilibration, and we're working on getting out some rate constants on that. Okay, so we've talked a little bit already about migration, neutron migration into the neck, and you can connect that back to looking at what happens with the derivative of the symmetry energy around normal nuclear density, and so that you get this larger derivative with the ASI-stiff and larger isospin migration effects. Some nice comparison to the Camara data, where you can then look at light fragments and the isotopic ratios for here that are, where you have this enhanced neutron richness in these fragments at mid-velocity. Oh, and so here's some very nice data where they have the PLF, the TLF, and the neck-like source. And again, you have this enrichment. When you have the biggest enrichment when you're aligned, much like you saw with the Indiana data, and then you can see this alignment and the neutron enrichment, and an agreement again sort of with a stiff symmetry energy. You can look at different reaction mechanisms. You can look at dynamical versus statistical type breakup, and then again make some comparison, sorry, to an ASI-stiff or an ASI-soft equation of state. One can look here again, looking at the different reaction mechanisms here in terms of incomplete fusion or binary reactions, and certainly as you look here for your neutron-rich system, you see a much better agreement with your ASI-stiff when you're looking at the mass of the light over the mass of the total. So then transverse collective flow. So we started in the very beginning looking at flow to just get some constraints on the equation of state before we were really worrying about the symmetry energy. Zach Coley came back and looked at transverse collective flow to try to put some constraints on the symmetry energy. And so this is his experimental data here in blue, comparison to an AMD calculation that again says the soft, which is the one that curves way over, is very much not in agreement. The stiff is in better agreement. Took this very same data and then compared it to not only the AMD, but the COMD and the SMF, and you get some nice agreement here in the fact that you have some constraints in L that look like you're somewhere in the vicinity of 70 to 80. Okay. Other things that people have looked at is the dipole degree of freedom, and again, you have some nice data here and the comparison to different equations of state. This was shown, I guess maybe it was shown in a parallel session, looking at the dipole strength and looking at the Pygmy dipole resonance versus the GDR. With the GDR, you see a shift both in the energy and the strength. In the Pygmy dipole resonance, you have a difference just in the strength. And so whether this becomes, again, a possibility that we'll be able to see, one has to take it from the theory and get an experimental measurement. again, ternary breakup is something that there's been some nice calculations that say we have deformed fragments, that we have this breakup, and how can we then take this and make the comparison to the data. And there's been some comparison to data here with the Chimera data. And then some nice work looking at these projectile-like, target-like properties, and really looking at spherical fragments versus deformed fragments, and the prediction that when we have ternary breakup of these neutron-rich systems, that this is then sensitive to the symmetry energy, and you can see the difference between the ASI-stiff and the ASI-soft. And although that looks really nice, if you actually go and try and measure that, by the time you get through your experimental filters and stuff, it gets a lot harder to measure. And so one thing that was done with the SMF was sort of this idea of using R-matrix theory to do a more sophisticated analysis, where here you are looking at this quadrupole moment and the octupole moment, where again, you see this small difference between the ASI-soft and the ASI-stiff. You see a small difference when you look at A and Z. When you do this combined analysis where you take all four of these and put them together and you come up with a value, you get a much better separation between the SIR values. So we talk about sifting through the remnants and this cut off, okay. This idea that we have very sophisticated detectors, we have very sophisticated theoretical models, and now we need to maybe borrow some techniques from other things. This was borrowed out of statistics, obviously, to be able to put some more constraints on our symmetry energy. Nice work looking to higher energies, okay? Work that was done at GSI, work that's going to be done at RIKEN, and some predictions that this may even matter for the quark gluon plasma people. Okay, so here's my summary, because I've just been cut off. That says there's lots of observables, there's lots of data, there is some overlap, and we obviously need to keep working both on the theory and on the experimental side, and we really need overlapping constraints to be able to understand what's going on. And this is a nice plot that really kind of shows not only the heavy ion collision constraints, but constraints from other things as well. And certainly we have to come back to the idea that there are constraints based upon things we do in the laboratory, but they also have to be consistent with astrophysical observations. And this observation of a solar mass neutron star started to put some constraints on some of the equations of state that could possibly explain it. Thank you for your attention.
Questions or comments? Yes.
Thank you, Sherry, for the nice talk. It's interesting to see that the investigation of isospin drift and diffusion after 30 years is still going on in so much detail. So let me maybe just ask, do you know meanwhile the energy dependence of the isospin relaxation time?
We know that you'll get the equilibration. We see more equilibration at lower energies, right? And as you go up in higher energies, you start to see non-equilibration. Is that quantified yet? No. But we obviously see that observation both in the theory and in the experiment.
From the beginning, you assume that the energy per neutron of asymmetric nuclear matter can be written in terms of just a quadratic term with respect to the isospin asymmetry. But in principle, higher power of the asymmetry parameter could be present. And if those are, have some, cannot be negligible, so all these analyses could change. So could you please comment on this?
Yeah, I mean, I think at this, there could be other orders. I think to this extent, we need to understand it to this power first, and then we can work on refinements later on, yeah.
Well, but if other terms are relevant, all the analysis with the experimental data is, I mean, the symmetry energy will not be will not characterize the equation of state of asymmetric matter. So,
okay, maybe I can interrupt here. Yeah, I think it's an important question. There are, as you know, there are theoretical predictions saying that the quotic term in the asymmetric expansion may be important, but so far nobody has studied what are the possible experimental effects. And obviously that's an important question. As a community, we need to look into it. Yes, it's an important question. Well, we have to move on. Let's thank Sarah again. Thank you.